Let's try another example or two of hypothesis tests with proportions. This example says in 1990, it was reported that 47% of households had a gun. In a survey conducted by the Gallup organization in the year 2000, 395 out of 1,012 adults aged 18 years or older said they had a gun in the house. Is there sufficient evidence to support the claim that the proportion of households that have a gun has decreased since 1990? Use alpha equals 0.05. Okay, so notice what happened. In 1990, 47% had a gun. They want us to see, they're claiming here, they want us to see if the proportion of households that have a gun has decreased. Now, decrease means gone down since 1990. So in 1990, the proportion was 0.47. We're trying to see if the proportion has gone down, has decreased from 0.47. That's the claim, is that it has. Okay? All right, well, let's look at our data. They went out and did a sample. They surveyed 1,012 people. And in that sample, 395 of them had a gun. So 395 out of 1,012. Okay, well, 395 out of 1,012, that's going to be our sample proportion, our p-hat. That's 0.39. Well, yeah, it looks like it has. It was 47%. In our little sample, we got 39%. So, yeah, that makes me think that the claim is accurate, that the proportion has gone down. But remember, every sample is different. Just because this sample of 1,012 people had a lower proportion than 47% does not mean a different sample of 1,012 people will be less than 0.49, less than 0.47. I could have just, gotten lucky. It could be a fluke that I just happened to get a sample where the proportion was less than 0.47. Okay? So our hypothesis test says, hey, how likely is it to have been under this 0.47? Did you just get lucky with the random sample of people that you picked? And that's exactly what a hypothesis test does. It tells us whether or not this was probably due to chance or whether the probability really has gone down below 0.47. Okay, the alpha they tell us to use is 0.05. Critical values come from the table. Since this is a left-tailed test, I know it's left-tailed because the less than symbol was in our alternative hypothesis. So 0.05. And we're doing a left-tailed test, so our critical value is negative 1.645. I'm going to get my test statistic from the calculator. Stat, test, option 5, 1-prop-z test. The proportion in my null and alternative hypothesis were 0.47. My X was 395 people out of 1,012. Said they had a gun in their house, so the N was 1012. Our symbol is the less than symbol. Our alternative hypothesis said that P was less than 0.47, so I'm going to pick the less than symbol. And I'm going to choose calculate. And again, notice it says p-hat's 0.39. Yeah, it should say that because that's what 395 out of 1,012 equals 39%. The Z is negative 5.08. I'm just going to round that to 2 decimals. Okay. And then let's go ahead while we're looking at it and let's go ahead and fill in the p-value. Now, remember p-value is the proportion or a percent or a probability. Pick your favorite p word. Okay. So this is a probability. Probabilities cannot start with 1. I've seen people that go, oh, 1 point, and they want to start writing it down. But remember, probability is always between 0 and 1. So when we see that 1.9 number, we go, wait, probability can't be more than 1. Look at the whole number. It's got a bunch of digits, and then it says E negative 7. Remember that E is how the calculator does scientific notation. So this really means 1.9 times 10 to the negative 7. That means that decimal should move left 7 places. When I do that, that decimal moves 7 places to the left from between the 1 and the 9. I will have 1, 2, 3, 4, 5, 6, 7. So it'll be a decimal and then 6 zeros and then a 1, 9. Okay? This is the probability. Notice it is very, very small. It's almost 0. Okay. All right, so coming back to our picture. Left tail test means we're going to have an area on the left. Okay. Significance is 0.05. Alpha is 0.05. That means we want to set, we want to know what test statistic or critical value, so the negative 1.645. That's the critical value that separates the 95% from the 5% in the tail. Okay. Now, where did our test statistic fall? Well, our test statistic was negative 5. That means it's 5 standard deviations to the left. Actually, a little bit more than 5 standard deviations to the left. Well, here's our z-score of 0, negative 1, negative 2, negative 3, negative 4, negative 5. Negative 5.08 is way down here in the tail. Okay? It is definitely in the rejection region. That means we will reject that null hypothesis. If you think about it from a p-value approach, you're comparing p to alpha. Well, p was 0.0000019. Alpha was 0.05. This p-value is way smaller than alpha. Remember, if the p is low, reject the whole. So we made the right decision in rejecting. The test statistic was in the rejection region. P is lower than alpha. We are rejecting. Okay, so what are we rejecting? We are rejecting the null hypothesis, the HO. That means we do not believe that 47% of households have guns. We are rejecting it in favor of the alternative. That means we are supporting the H1, the alternative hypothesis, that the proportion of homes who have guns is below 47%. Because if you think about it, this 0.39 that we got from our sample is quite a bit lower than 0.47. So if the proportion of houses who really do have guns is 47%, the chance of us getting a house or getting a sample where only 39% had guns is very low. It's unlikely to occur. So if it's so unlikely to occur, then this must not have been a true statement in our null hypothesis. Now, is there any guarantee that we're right? No. We could be wrong. We could be making a type 1 error and rejecting when we shouldn't have. But the probability of that is extremely low. So we're pretty confident. Okay? So what is our conclusion? There is sufficient evidence to support the claim. That what? And we write our claim. Okay? Now notice, this is exactly like the sentences I was writing previously, only I left out the word not. Remember, if we circle not to do not reject, then we write not. There's not sufficient evidence. I did not circle the word not, so I'm not writing the word not. There is sufficient evidence to support the claim that the proportion of homes who own a gun is less than 0.47. We are supporting this claim, okay? So are we supporting the claim? Yes, we are. Were there statistically significant results? Yes, there were. There's only statistical significance when you reject the null in favor of the alternative. Okay? Let's try another one. In clinical tests, I like this one because this is about, they really have to do things like this when they come up with new drugs or new treatments for medical issues, okay? In clinical tests of the drug Clarinex, now I don't know if this is really true for Clarinex, but anyway, 1,655 patients were treated with a 5 milligram dose of Clarinex, and 2.1% of them experienced fatigue. Fatigue means you get tired, and not just like, oh, I'm a little tired for a second. It's like, you experience some fatigue. You're real tired. Use use a 0.01 significance level, that is alpha, so alpha is 0.01, to test the claim that the percentage of Clarinex users experiencing fatigue is greater than 1.2%. the rate for those not using Clarinex. Okay, so here's what they're getting at. Sometimes medications have side effects, okay? So it's something that they didn't want to happen, is not part of the treatment plan, but it happens anyway. So for example, sometimes when you watch a medication ad for a new drug on TV or whatever, and at the very end they list all those terrible, horrible things that might happen to you if you take that medication. Okay? Sometimes I'm like, man, I would not take that medication if it meant I was going to have, that problem. Sometimes they're not so bad, sometimes they are. They are required to report those because when they did clinical trials like this, a significant number of people experienced that particular issue. Okay, so they need to tell you, hey, if you take this medication, this may happen. This may be a side effect that you experience. And they need to report that. Okay? All right, so apparently 1.2% is the rate of people experiencing fatigue who are not using Clarinex. So if we just went out to a whole bunch of people and said, hey, are you feeling fatigued today? And they said yes or no, 1.2% of them would say, yeah, man, I'm fatigued. I am tired. Okay? These are people that are not using Clarinex. So in theory, if we give a bunch of people Clarinex and the same percentage of people who experience fatigue, it's the same as those who were not taking Clarinex, then we just go, okay, well, it wasn't the Clarinex making them tired. 1.2% of people are always tired, no matter whether they're taking Clarinex or not. So Clarinex only needs to take responsibility for it if a higher percent of patients are experiencing fatigue than the general population. 1.2% of all people are going to be experiencing fatigue. They're going to be tired. So if the Clarinex users, it's still 1.2%, then we go, hey, it's not Clarinex's fault. They were already tired. Okay? But if higher than 1.2% of people who are taking Clarinex are feeling real tired, then we got to go, maybe the Clarinex was causing it. Maybe the Clarinex is to blame, and we need to put a warning label on our Clarinex pills that it could cause some fatigue. So that's what we're trying to figure out, okay? So our null hypothesis is going to be, hey, the proportion of people who are tired is 0.012. Now, where am I getting that from? 1.2% as a percent has to be converted to the decimal, and a decimal of 1.2% is 0.012. All right. Our alternative, our claim, okay, they are claiming that the percent of Clarinex users experiencing fatigue is greater than 1.2%. So greater than 0.012. Because we chose greater than, it is a right-tailed test. Okay. My critical value. Well, my critical value is alpha level 0.01. This was a right-tailed test. It's going to be 2.33. So I know on my picture over here, right-tailed tests over on the right edge, my cutoff number or critical number is 2.33. I just need to see if my test statistic is in the rejection region or not. Okay? Calculator is going to tell me my test statistic. So stat, test, option 5 for 1 prop Z test. Great. Our P naught, our proportion number in our null and alternative hypothesis is 0.012. And now we have an issue. It is asking us for the X and for the N. And if you read back through this prompt, they never tell us one of those numbers. They say 1,655 patients were treated and 2.1% of them experienced fatigue. Okay, well, then the N is 1,655. That's how many patients got the medicine. But they did not tell us how many experienced fatigue. So we're going to have to do a little thinking about that, okay? Now, they told us 2.1% experienced fatigue. Well, if 2.1% of the 1,655, then that's going to tell us what our X is, okay? 2.1% of the 1,655. All right, so I'm going to exit out of my test for just a second because I got to find X. A couple ways you could do that. You could convert the percent to a decimal, so 0.021, and multiply that by 1,655. And that's 34.755. You probably did not have 34.7 people that were tired. It was probably the full 35 people. Another option, if you like proportions, is to say X out of 1655 equals 2.1 for 2.1% out of 100. And then cross multiply and divide. You could do that too. 1655 times 2.1 divide by 100, and you're still going to get that 34.75. Okay, so 35 people are experiencing fatigue. That's going to be my X. So in my stat test, option 5, my P0 number, 0.012, my X is 35, because 35 out of 1655 is that 2.1%. Okay. I'm going to pick the greater than symbol, because I'm trying to see if the proportion of people who use Clarinex, if there's a higher percentage of tired people than those in the regular population. And notice our P hat was the 2.1%. They're putting 0.02 here, 0.021, because that's the decimal of 2.1%. So in the regular population, 1.2% of people experience fatigue. In our Clarinex study, 2.1% of people experience fatigue. Not looking good for Clarinex. A higher percentage are experiencing fatigue than in the general population. The question is it high enough percentage to put us in our rejection region and make us go, you know what? Reject the null, believe the claim. That means, ooh, yeah, Clarinex users do get more tired. They have more fatigue. All right, so what did we get? Well, our test statistic, our Z value was 3.42. Where is 3.42? Well, it's in our rejection region. It's past 2.3. It's about right here. So we will reject because it is in the rejection region. Let's go ahead and look at the p-value as well. The p-value, notice it looks like it's 3.1, but if you look all the way to the end, it's got that little e. So 3.1 times 10 to the negative 4. When I move that decimal 4 places left, I'll have 0.00031. So really, I'm comparing p to alpha. 0.00031 is definitely smaller than 0.01. P is low, so we were right to choose reject. Okay? All right, so that means we are rejecting the null. That means we're supporting the alternative. We're supporting the claim. We do believe that the proportion of Clarinex users is going to be higher. The proportion of Clarinex users who experience fatigue is going to be higher than 1.2%, the normal 1.2% of everyday people that experience it. So we are blaming that on the Clarinex. Okay? All right, so our conclusion, there is sufficient evidence to support the claim that the proportion or percentage, I'll say percentage because I think that's how it was written, percentage of Clarinex users who experience fatigue is greater than 1.2%. Okay? That means Clarinex really does need to put a label on their packaging that it could cause fatigue. Now, most of us go, 2.1%, that's not very high. Okay? And maybe it's not to you. You know, maybe to you it's like, well, it's just a small chance. 2.1%, that's not a very high chance that I'm going to experience fatigue. I think it's fine. I'm going to chance it. Okay, great. But keep in mind, if your job is, you know, operating heavy machinery or truck driving or something, that could put people at risk if you were to fall asleep. So, you know, they need to let people know that it could happen. So probably what you would want to do is if you felt like, it's worth the risk, I'm going to try it, you might want to try it on a day when you're not doing something that could be dangerous if you fell asleep. And then if you saw, hey, I didn't experience fatigue, doesn't seem to be a problem for me, then you know, and you could take it maybe other times. But you have to know that it's a possibility that it could happen. Okay? All right, so are we supporting the claim? Yes, we are. We rejected the null. That means we are supporting the alternative. And yes, we found statistically significant results. Okay, we mentioned in 10.1 that there was a third method. So far we've been using rejection region and p-values to make our decision, and we noticed that rejection region and p-value always lead to the same conclusion. Whether it's reject or do not reject, they always lead to the same conclusion. But there was a third way that we could make our conclusion, and that was with confidence intervals. Okay, so let's say we're working with proportions. Okay, remember, a confidence interval tells you the how confident, or I'm sorry, at a certain level of confidence, 90% confidence, 95% confident, whatever, that the true proportion of the population is between whatever and whatever. Okay, so let's say that my null hypothesis was p equals 0.12. Maybe that's 12% of the population likes, let's see, like spinach. Okay, I would think portion of people who like spinach is probably low. I don't like spinach. All right, so let's say that p is 0.12. That's pretty low. Then my alternative would be, hey, proportion is not 0.12. Now, this really only works when you're doing two-tailed tests, when you have the not equal to. Okay, all right, and they're using alpha equals 0.05. Not well, if alpha equals 0.05, that means there's 95% confidence, right? Because the 95% confidence and 0.05 add up to 100%. All right, so let's say you do your 95% confidence interval, and you get this. Okay, well, again, if this is the proportion of people who like spinach, we would be saying we are 95% confident that the true proportion of people who like spinach is between 0.08 and 0.16. So between 8 and 16% of people like spinach. That's what we would be saying. So are we going to reject or not reject the null hypothesis? Well, 0.12 is in this interval. 0.12 is between 0.08 and 0.16. If we're 95% confident that between 8 and 16% of people like spinach, 12% is right in there. So that means we would not reject this null. We don't necessarily believe it. We can't always, we can't support the null, but we either reject it or we don't reject. And we would not reject because 12% is in that interval. Okay? So we will not reject it. Now on the flip side, let's say that we had done a 95% confidence interval and it gave us the results 0.13 to 0.19. Well, notice 0.12 is not in this interval. Okay, if this is saying, hey, we are 95% confident that between 13 and 19% of people like spinach, well, 12% is not in there. So that means we are not going to support this null hypothesis. We're going to reject it. Okay? Another example. Let's go back to, in order to use this confidence interval approach, we need to use a two-tailed test. So I'm going to come back to this one. This was the one about the percentage of females who lived alone. That was our two-tailed test. Okay. So remember, out of our 500 people, 500 females in the survey, 285 lived alone. Okay, so let's go back and let's do a 95% confidence interval. So stat, test. Remember option A, if you look back at your chart, if you're doing a confidence interval in proportions, you pick one prop Z int. That's option A. And we say, hey, 285 out of 500 women live alone. We were doing 0.1 for alpha. That means 0.9 is our confidence level. Remember, alpha and your confidence level have to add up to 1. And our confidence level would be 0.53358 up to 0.60642. Okay, so remember, that means we are 90% confident that between 53% and 61% of females live alone. Well, 53% to 61% does contain 58%. 58% is in that interval. So we would not reject the 58%. So notice that all three methods, the test statistic method with our rejection region, our p-value approach and our confidence interval approach would all lead to the same conclusion of not rejecting. Okay, so we just wanted to see an example of kind of how that confidence interval approach worked. Notice another thing here. We mentioned that statistical significance. Remember all these times that we said, was there statistically significant results? We said yes when we rejected. Okay, we're going to see an example of this in 10.3, but here's the issue. If you have a really, really, really large sample, okay, that will increase your chance of rejecting a null hypothesis. Okay, you'll see why in 10.3. But sometimes you have to think about if it's practical. Okay, you know, maybe, let's go back to this Clarinex example. Maybe instead of a 1.2% probability, maybe our test results, our sample, had been 0.013. Well, 0.013 is greater than 0.012, but does it really matter whether it's 1.2% or 1.3%? So it could be a case where you reject and you say that there's statistically significant results, but the difference is so small that it doesn't really matter. And we'll see an example of that in 10.3, but I just wanted to plant that seed that it is something that we have to think about.